Look up at any skyscraper, and you see glass and concrete. But hidden behind those walls, invisible to everyone on the street, is the real structure holding everything up. Steel beams shaped like the letter I. These I-beams carry loads measured in thousands of tons, supporting buildings over 1,000 feet tall. Yet most people have no idea how they're made. The process starts with iron ore blasted from mountains, melted at 3,000 degrees Fahrenheit, and rolled through massive machines that shape glowing metal into precise structural members. This is how America builds the backbone of modern infrastructure. The I-beam revolutionized construction in the late 1800s, when engineers discovered this shape could support far more weight than solid beams while using less steel. Most material concentrates in the top and bottom flanges, where bending stress is greatest, while the thin web connects them. By 1900, steel I-beams enabled skyscrapers like the Empire State Building and bridges spanning thousands of feet. Today, the global steel beam market exceeds $32 billion annually. Production begins at iron ore mines in Minnesota's Mesabi Range and Michigan's Upper Peninsula. Mining companies strip away hundreds of feet of overburden using hydraulic excavators and haul trucks as tall as houses. Geologists locate ore bodies with 60 to 70% iron concentration. Drilling crews bore holes dozens of feet deep, pack them with explosives, and detonate in sequence to fracture the rock. Front-end loaders scoop the broken ore into haul trucks carrying 300 tons per load. These trucks make continuous trips from pit floor to crushing facility, moving millions of tons annually. In underground operations, ore travels on conveyor belts through tunnels supported by steel beams. The irony, they're mining the raw material for the beams that keep them safe underground. At the crushing plant, primary crushers reduce rocks to gravel using steel jaws with thousands of tons of force. Multiple crushing stages reduce size until particles measure about 1 inch across. Vibrating screens sort continuously. Correct particles advance, while oversized chunks return to crushers. This runs 24/7, producing uniform feedstock for steel making. The crushed ore moves to steel mills where transformation begins. Blast furnaces, towering over 200 feet tall, mix iron ore with coke and limestone, then blast superheated air through at 3,000 degrees Fahrenheit. The reaction separates iron from oxygen, producing molten iron that pools at the bottom. A single blast furnace produces over 10,000 tons daily, running continuously for years between shutdowns. Electric arc furnaces offer an alternative, melting scrap steel using massive electrical currents. 3 graphite electrodes lower into a vessel filled with scrap metal. When electricity arcs between electrodes and metal, temperatures reach 3,500 degrees Fahrenheit. Modern furnaces process a complete batch in less than 2 hours, more flexible than blast furnaces for smaller runs. Molten steel requires refining to remove impurities and adjust composition. Workers add alloying elements like manganese and chromium to increase strength. Oxygen burns away excess carbon, while slag-containing impurities rises for skimming. Structural steel typically contains 99% iron, with carefully controlled carbon and manganese. Refined molten steel flows into continuous casting machines that form solid billets. The caster pours liquid steel into a water-cooled copper mold that solidifies the surface while the interior remains molten. As steel solidifies, it's continuously pulled downward at 3 feet per minute. The emerging billet measures about 12 inches square and stretches hundreds of feet before cutting. Torches cut the continuous billet into lengths of 20 to 40 feet, which move to storage yards. These billets retain significant heat and must cool gradually to prevent cracking. Quality inspectors examine each billet for surface defects and dimensional accuracy. Approved billets advance to reheating furnaces, while rejected ones return for remelting. Reheating furnaces bring billets to rolling temperature around 2,200 degrees Fahrenheit, hot enough for malleability. Billets travel slowly through increasingly hot zones for even heating throughout. Natural gas or fuel oil burners line the walls, with computer systems adjusting flames based on temperature sensors. A billet spends 1 to 2 hours in the furnace before emerging glowing orange-red. The rolling mill is where transformation happens. A glowing billet enters where massive steel rollers squeeze down with thousands of pounds per square inch. The billet elongates and thins, traveling to the next stand, where rollers squeeze again from different angles. Modern mills contain 10 to 15 stands, and the journey from square billet to I-beam takes less than 2 minutes across over 1,000 feet. The transformation from square to I-beam happens gradually. Early stands flatten and stretch, reducing thickness while increasing length. Middle stands form the web, and flanges using specially grooved rollers. Final stands refine dimensions, ensuring the web is vertical and flanges are parallel, maintaining tolerance within fractions of an inch. Temperature control during rolling is critical. Steel must stay hot enough to deform without cracking, but cool enough to hold shape. Water sprays between stands wash away scale and control temperature, creating massive steam clouds. By the final stand, the beam cools to around 1,500 degrees, still glowing red, but solid enough to maintain its eye shape. The hot beam travels onto a cooling bed with hundreds of steel bars that support while allowing air circulation. Fans blow ambient air across the beam, gradually reducing temperature over 20 to 30 minutes. Cooling must happen slowly and evenly to prevent warping or internal stress. Some mills use controlled cooling patterns, where different sections cool at different rates for specific strength properties. Below 1,000 degrees, beams enter heat treatment for final strengthening. Quenching with water or oil creates harder surfaces while interiors remain ductile. Tempering follows, reheating to 800 to 1,000 degrees to relieve stress. Exact treatment depends on intended use. Earthquake zone beams receive different treatment than cold weather beams. After heat treatment, beams move to the straightening press. Some beams develop slight curves during cooling. Hydraulic rams apply controlled force at specific points, bending the beam back to straightness. Laser systems calculate exactly where and how much force to apply, checking alignment after each adjustment. The cutting station uses industrial bandsaws with carbide-tipped blades, traveling at 3,000 feet per minute. Computer systems measure each beam and calculate cutting positions based on customer orders. Most beams are cut to standard lengths, 20, 30, or 40 feet. A single blade cuts through a 2-foot tall I-beam in about 5 minutes. Quality control begins before inspection, with operators collecting samples throughout production for laboratory testing. The quality lab crushes test pieces to measure yield strength and tensile strength, typically over 50,000 pounds per square inch. Metallurgists examine samples under microscopes to verify grain structure. Charpy impact tests measure toughness by striking notched samples with a weighted pendulum. Visual inspection catches surface defects. Inspectors look for cracks, scratches, or laminations. Automated cameras scan the entire surface while ultrasonic testing detects internal voids. Only beams passing all tests receive certification stamps. Approved beams move to finishing where workers grind away scale or rough spots. Some beams receive protective coatings, paint, galvanizing, or fire-resistant materials. Galvanizing dips the beam into molten zinc at 850 degrees, creating rust protection for decades. Painted beams pass through automated spray booths, applying primer and top coat. The packaging area handles beams weighing several tons. Overhead cranes with electromagnetic lifters move beams to the storage yard. Workers bundle matching beams together, typically 8 to 12 per bundle, securing them with steel strapping. Each bundle gets tagged with specifications, heat number, and destination. Transportation requires specialized equipment. Flatbed trucks carry shorter beams, while longer beams need extendable trailers. Rail transport moves thousands of tons at once on flat cars. Loading must prevent movement. Multiple straps and chains hold everything immobile to prevent accidents. The largest American steel beam mills include Nucor in South Carolina and Arkansas, Steel Dynamics in Indiana, and Cleveland-Cliffs across the Midwest. These mills produce millions of tons annually, operating around the clock with computerized controls. Modern mills use 1/3 less energy per ton than older plants. Research focuses on higher strength steels that allow smaller beams to carry the same loads, reducing material use. From iron ore buried underground to I-beams supporting skyscrapers. From 3,000-degree furnaces to precision rolling mills. From square billets to structural members shaped exactly for maximum strength with minimum material. Every steel beam represents a chain of controlled transformations: mining, crushing, melting, casting, rolling, cooling, treating, cutting, testing, and shipping. These beams quietly hold up the world we've built. Thanks for watching. Hit that like button and subscribe for more stories about the industrial processes building America's infrastructure. See you next time. Walk into any hardware store and you see ordinary bolts and nuts, small fasteners you can hold in your hand. But in industrial facilities across America, engineers rely on fasteners measuring 3 feet long and weighing over 100 pounds, holding together structures that carry loads measured in thousands of tons. These giant bolts and nuts secure wind turbine towers 500 feet tall, clamp together sections of oil drilling platforms in the Gulf of Mexico, and bolt the structural steel of bridges spanning entire rivers. The process creating them starts with high-strength steel billets, so precise that tolerances measure in thousandths of an inch. This is how America makes the fasteners holding modern infrastructure together. The global fasteners industry exceeds $90 billion annually. With a single bolt for a wind turbine can cost $500, while specialty bolts for offshore platforms run thousands each. American manufacturers, including Fastenal, Portland Bolt, and Nucor Fastener, produce millions yearly. They meet strict standards set by ASTM International and SAE into precise lengths. Bolt billets measure twice as long as nut billets. Each cut must be perfectly square and clean, avoiding burrs that would affect later operations. Cutting coolant sprays onto the cutting zone, reducing heat and flushing metal chips. Computer controls measure each billet automatically, ensuring specifications within fractions of an ounce. Workers stack cut billets on pallets, separating bolt billets from nut billets for different processing. Quality inspectors examine random billets from each batch, checking for surface defects and proper dimensions. They use calipers to verify diameter and length, then mark each batch with heat numbers tracing to the steel mill. This documentation follows billets through every stage, creating complete records. Approved billets advance extends out. The press forces hot metal sideways, forming the hexagonal bolt head. High-temperature lubricant sprays onto the die before each strike, preventing the hot steel from sticking. When lubricant contacts the die at over 1,000 degrees, it vaporizes and forms a protective barrier. After cleaning, workers sort parts by size and transfer them to the marking station. Each bolt and nut receives identification stamps showing strength grade, manufacturing standard, and maker's mark. For nuts, stamps go on hexagonal faces. For bolts, on the heads. Thread rolling forms threads through cold plastic deformation rather than cutting. The bolt shank passes between two hardened steel dies engraved with thread profiles. As dies, some facilities perform magnetic particle inspection to detect invisible surface cracks. The bolt is magnetized and dusted with iron powder that accumulates at crack locations. Button and subscribe for more stories about the manufacturing processes holding the modern world together. See you next time. Picture this: a vessel longer than a football field, weighing nearly 8,000 tons, powered by a nuclear reactor that will run for 33 years without refueling. It can dive to depths where the pressure would crush a car like a tin can. It carries enough firepower to level a city. And it's so quiet, it's literally quieter than the background noise of the ocean itself. Building a nuclear-powered attack submarine is one of the most complex engineering challenges on Earth. Only 2 facilities in the entire United States possess the technology, security clearances, and expertise to do it. The construction process takes over a decade, costs $3.4 billion per vessel, and involves thousands of workers sworn to secrecy. Today, we're going inside those facilities to see how America builds the most advanced submarines ever created. This is the story of turning steel and science into invisible ocean predators. But first, we need to talk about the man who made it all possible. Admiral Hyman G. Rickover, a name most Americans have never heard, but who changed naval warfare forever. Born in Poland in 1898, Rickover immigrated to America as a child. He joined the Navy, became an engineer, and in the 1940s, he became obsessed with a radical idea: nuclear-powered submarines. The Navy brass thought he was crazy. Nuclear reactors were massive, dangerous, barely understood. Putting one inside a submarine seemed impossible. Rickover didn't care what they thought. He was famously difficult, demanding, and absolutely relentless. He personally interviewed every officer who wanted to serve on nuclear submarines. These interviews became legendary. He'd ask impossible questions, create uncomfortable silences, test people's breaking points. One future submarine commander reported sitting in complete silence for 2 hours while Rickover read paperwork. But it worked. Rickover built a culture of absolute excellence and zero tolerance for mistakes. In 1954, the USS Nautilus, the world's first nuclear submarine, went to sea. It revolutionized naval warfare overnight. Submarines could now stay submerged for months instead of hours. They could travel underwater at speeds conventional submarines could only dream of. Rickover ran the Navy's nuclear program for 63 years, longer than any military officer in American history. When he finally retired in 1982, at age 82, he'd built the foundation for everything we're about to see. Fast forward to today. The United States Navy operates the most sophisticated submarine fleet on the planet, and they're all built at just 2 shipyards: General Dynamics Electric Boat in Groton, Connecticut, and Huntington Ingalls Newport News Shipbuilding in Virginia. Let's focus on the Virginia-class attack submarine, the backbone of America's underwater fleet. These vessels represent the cutting edge of submarine technology. At 377 feet long and displacing 7,800 tons when submerged, they're massive. But size barely hints at the complexity. Construction doesn't start with laying a keel like traditional shipbuilding. Modern submarines are built in modules, massive sections constructed separately and then joined together. Think of it like building the world's most complex and expensive Lego set, where each piece weighs hundreds of tons and costs millions of dollars. It begins in fabrication shops across the facility. Workers cut and shape special high-strength steel called HY80, capable of withstanding extreme pressure at depth. These aren't thin sheets. We're talking steel plates 4 to 6 inches thick in some areas. Cutting and welding this material requires specialized equipment and certified welders who've spent years training. The hull sections start taking shape in massive assembly buildings. The submarine's hull uses a cylinder design, the strongest shape for resisting pressure from all directions. Workers install thousands of components inside each section before the modules get sealed. Piping systems, electrical conduits, equipment mounts, ventilation, all precisely positioned. Here's something most people don't realize. Submarine construction is measured in years, not months. A Virginia-class submarine takes 10 to 12 years from first steel cutting to delivery. Why so long? Every single weld gets X-rayed. Every system gets tested multiple times. One tiny defect in a weld could mean catastrophic failure at depth, where the pressure exceeds 800 pounds per square inch. The most critical and secretive module is the reactor compartment. This sealed section houses the S9G nuclear reactor, the beating heart that powers everything. The reactor details are highly classified, but we know the basics. It uses enriched uranium fuel, generates heat through nuclear fission, which creates steam to drive turbines, which generate electricity and turn the propeller. And here's the crazy part. This reactor will run for 33 years without refueling. The submarine will be retired before the reactor needs new fuel. That's the equivalent of buying a car that never needs gas for its entire operational life. Once the major modules are complete, the real challenge begins: joining them together. This happens in a massive indoor facility, where overhead cranes can lift hundreds of tons. Workers position each module with precision measured in fractions of an inch, then weld them into a single hull. The welding process is critical. Welders work in teams, often in cramped spaces, joining sections with welds that must be absolutely perfect. After welding, every seam gets ultrasonically tested, X-rayed, and pressure tested. The hull must be completely watertight, because at operational depths, even a pinhole leak would let water in with enough force to cut through steel. Next comes one of the most distinctive features, the anechoic coating. Workers apply thousands of rubber tiles to the submarine's exterior. These aren't decorative. Each tile is precisely engineered to absorb sonar waves, making the submarine incredibly difficult to detect. The exact composition and design of these tiles is classified, but they're a major reason Virginia-class submarines are quieter than the ambient noise of the ocean. Inside, the submarine is being fitted with systems that will keep 135 crew members alive for months underwater. The atmosphere control system is remarkable. It takes seawater, runs it through electrolysis to produce oxygen, and scrubs carbon dioxide from the air using chemical reactions. The crew breathes manufactured air hundreds of feet below the surface. Water systems are equally sophisticated. Distillation equipment converts seawater into fresh water for drinking, cooking, and the reactor cooling systems. A Virginia-class submarine produces thousands of gallons of fresh water daily, enough for the crew and all onboard systems. Food storage is carefully planned. Submarines carry enough provisions for 3 months, stored everywhere including under crew bunks. The galley operates 24/7, serving 4 meals daily to accommodate different watch schedules. Now let's talk about weapons. Virginia-class submarines carry a deadly arsenal. 12 vertical launch tubes in the bow can fire Tomahawk cruise missiles, capable of striking targets over 1,000 miles away with precision guidance. 4 torpedo tubes fire Mark 48 torpedoes, the most advanced submarine-launched weapons in existence. The torpedo room isn't just about firepower. It's where torpedoes are loaded, maintained, and prepared for launch. Each Mark 48 weighs nearly 3,700 pounds and costs over $3 million. The room includes sophisticated loading equipment, testing systems, and safety mechanisms, because you're dealing with high explosives in a confined metal tube underwater. The control room represents the technological heart of the submarine. Unlike old submarines with periscopes and mechanical controls, Virginia-class subs use photonics masts, essentially high-definition cameras on retractable masts that feed images to screens. The helmsman and planesmen control the submarine using joysticks, not wheels and levers. Sonar systems fill an entire room with computer screens and sophisticated signal processing equipment. Trained sonar technicians can identify specific ship types from hundreds of miles away just by analyzing the sounds those ships make. The sonar sphere in the bow contains thousands of hydrophones working together to create an acoustic picture of the ocean. Communication at depth is challenging. Radio waves don't penetrate water. Submarines trail a wire antenna near the surface to receive very low-frequency transmissions. For two-way communication, they must come to periscope depth or surface. After years of construction, the submarine is finally ready for launch. But launching doesn't mean it's done. Not even close. The submarine enters a pier alongside the construction facility, where workers install final systems, load provisions, and conduct countless tests. Then comes sea trials, where the submarine leaves the pier for the first time under its own power. For weeks, the crew and shipyard personnel put every system through rigorous testing. Deep dive tests verify hull integrity. Speed trials push the propulsion to maximum capacity. Weapon systems fire test shots. Everything that can be tested gets tested. During sea trials, problems always emerge. A valve doesn't seal properly. A computer glitches. Instruments read incorrectly. The submarine returns to the pier, workers fix the issues, and trials resume. This process repeats until every system meets Navy specifications. Only after passing all tests does the Navy officially accept the submarine. A commissioning ceremony marks the submarine's entry into active service. From that moment, it becomes a Navy asset, ready for missions anywhere in the world's oceans. The construction process never stops. Electric Boat and Newport News are already building the next generation, Columbia-class ballistic missile submarines. These will replace the aging Ohio-class boomers that carry America's sea-based nuclear deterrent. Columbia-class submarines are even larger and more complex than Virginia-class boats. At 560 feet long and displacing 21,000 tons submerged, they're true underwater behemoths. Each will carry 16 Trident II. 2 ballistic missiles, each missile capable of carrying multiple nuclear warheads. The first Columbia-class submarine, the USS District of Columbia, is currently under construction with delivery scheduled for 28. The program will ultimately build 12 of these submarines at a total cost exceeding $100 billion, making it one of the most expensive military programs in history. Technology continues advancing. Engineers are developing air-independent propulsion systems that could extend underwater endurance even further. New stealth coatings make submarines quieter. Advanced sonar can detect threats at unprecedented ranges. Automation reduces crew requirements. But some things never change. The fundamental challenge remains the same. Build a vessel that can survive in one of the most hostile environments imaginable, operate for months without support, and project American power anywhere in the world's oceans. From Admiral Rickover's vision to today's Virginia-class submarines, America has maintained technological superiority underwater for 70 years. Thousands of workers across 2 shipyards continue that tradition, building submarines that will patrol the oceans for the next 3 decades. So next time you look out at the ocean, remember, somewhere beneath those waves, a Virginia-class submarine might be passing by. You'll never hear it. You'll never see it. But it's there, a testament to American engineering and the thousands of skilled workers who built it piece by piece, weld by weld, over a decade of meticulous construction. From steel to silent hunter. Thanks for watching. Hit that like button and subscribe for more incredible stories about how America builds the most advanced military technology on Earth. See you next time.